Hi, I'm Kelly Providence, trainer for Solargen. In this video we're going to show you how to calculate for circuit ampacity requirements. The first thing we want to do is find out what the continuous current is of the circuit, and for PV source circuits, for the PV module and the PV module strings, we have to calculate this maximum continuous current. The manufacturer provides us with the short circuit current, the ISC, and that's based on 1,000 watts per square meter irradiance. The fact is the irradiance can be higher than that, so the National Electrical Code directs us to make a calculation to compensate for that. So they said let's go with 1,250 watts per square meter. So we take the ISC times 125%, and that gives us the maximum continuous current. Once we've done that, then we have to calculate for the actual circuit requirements for this continuous current rating. We want to make sure that we don't overload the circuit, so one of the precautions that we take, and as directed by the National Electrical Code, is to size the circuit 125% greater than the continuous current. So now we multiply by another 125% and we get our circuit ampacity requirements. So the first step, we took our short circuit current, which we got from a module data sheet. So we look at the Solar World data sheet for the 275 watt module, scroll down to the ISC, and there it is, 9.58 amps. So we take the 9.58 amps times 125% gives us 11.975 amps continuous current. Next step, take that continuous current, multiply by another 125%. That gives us 14.97, or approximately 15 amps. And at this point we want to look for a conductor that's rated for that ampacity, and we go to the table 310-15B16. Let's take a look at that table. And here we have multiple columns and a lot of different conductors to look at. We're just showing conductors from number 18 down to number 4 in this section of it. We're showing copper conductors and aluminum conductors. We're going to use copper, and we have 3 columns in the copper: the 60-degree rated wire, 75-degree rated wire, and 90-degree rated wire. Now this is Celsius that they're giving us to. Which cable are we using? Well, I'd say 99.9% of the time you will be using a 90-degree rated cable. So this is typical of what we use in PV systems. However, especially with residential systems, this is however, the equipment that we're actually tying into is 75-degree rated. For commercial systems, occasionally you'll find some 90-degree rated equipment. In that case, you could use this column. But for residential systems, all of it on the DC side is 75-degree rated, so we're going to use this column for our ampacity requirement. We see that the first conductor ampacity we see is number 14. So a number 14 American wire gauge is rated 20 amps. So we select this conductor, plug it into our formula, and what we need to do now is determine the actual environment in which the conductor is going to be placed. This table, 310-15B16, is based on 3 conductors and a conduit, no more than that, and it's also based on an actual temperature of 30 degrees C, 86 degrees Fahrenheit. If the environment in which the conductor is going to be installed is greater than that, then we have to derate the conductor. And if we run more than 3 conductors in a conduit, we have to derate for that as well. So in this instance, for this example, we're going to use an attic temperature of 110 degrees Fahrenheit and 4 conductors in a conduit. So we actually have 2 parallel strings running together through this conduit down to the inverter. So we look in these 2 tables to find what our derate factors are. Let's take a look at those. Our temperature correction table shows us that for 110 degrees we have a 0.87 derate factor. Now you'll notice I'm using the actual column of the conductor that I selected instead of the equipment. So this is the conductor we're derating. So 0.87 is the derate factor. Let's take a look at what we have to do for more than 3 conductors in a conduit. Shows here if we have 4 to 6, 80%, we reduce the ampacity to 80% of it. So this is what we're doing. We're doing 4 in a conduit, so we have this derate factor. Let's go back, take a look. We multiply the 20 amps, which is what that number 14 conductor is rated, times 0.87 times 0.8 gives us 13.92. So that's the actual ampacity of the conductor now with the environment that we've placed it in. Is it okay? Is it good enough? Or do we have to go to a larger conductor? Well, we compare that number to the continuous current that we calculated up here in step 1. And since the 13.92 is still greater than 11.975, it's okay. So we're in good shape. There's an alternate way to make these calculations. You could have taken the continuous current divided by each one of these derate factors, and that gives you the ampacity requirement of the conductor, which of course is 20 amps. So that's another way to look at it. Next thing, the overcurrent device. So we use the same number. This is what we found our conductor number 14 with, and we're also going to use this to find our overcurrent device if we have to have one. So we want to look at the incremental availability of overcurrent devices. So let's take a look. It shows in Article 246A that this is the increment of overcurrent device available from manufacturers. So it shows 1 through 10 amps we have 1 amp increments, and then we have a 12 amp fuse, and then a 15 amp, 20 to 25, 30. So we'll always refer to this table when selecting overcurrent device. So a 15 amp would be the appropriate overcurrent device. So that's pretty much it. That's calculating and determining the ampacity requirements of the circuit. If you were doing an inverter circuit, it's all the same. The output continuous current is provided to you by the manufacturer, so you can see that on the data sheet or on the label. You don't have to calculate that step 1 up here if you're calculating for inverter output. Well, thank you very much. I hope that was helpful. Have a good day.